radar blip you see here is detected by a Simulink signal processor. And the aircrafts on this camera feed are all flown by Simulink Autopilot. Both are auto-generated to Portable C, and both are running inside the game engine right now. Let me show you how. So 2 independent Simulink models. The first one I'll show you is the Autopilot. 6 root inputs. At the top, phi command, theta command, and v command. Phi, theta, and v for the aircraft's current state. And 3 root outputs at the bottom for the control surface commands, the aileron, the elevator, and the throttle. And inside, 3 cascaded PID controllers, the bank hold, the pitch hold, and the airspeed hold. Each one takes a command set point, subtracts the current value, runs a PID, saturates to the control surface envelope. Just standard cascade autopilot architecture. And if we open up PID phi, you'll notice these are only PD controllers on the inner loops, no integral term. The outer heading and altitude controllers already handle steady state error, so adding I here would just cause windup. Okay, now cutting to the second independent model, a complete pulsed radar signal processor, 3 MATLAB function blocks in series, MVDR beamforming, Range-Doppler processing, CFAR detection. All authored so that the generated C is pure ANSI with no phased array toolbox dependency. The input is a raw IQ cube, 2500 range samples, 8 antenna elements, and 16 pulses per coherent processing interval. Then, the beamformer stage. This collapses the 8 elements down to 1 channel, using a minimum variance distortionless response weight vector. Adaptive beamforming that nulls interferers spatially. Then comes the Range-Doppler stage, which does the matched filter against the transmit chirp reference. Then a Hamming windowed FFT across the 16 pulses to resolve target velocity. And then heading to the CFAR stage. This does the cell averaging constant false alarm rate detection, to ultimately threshold the Range-Doppler map and pull out the top 16 targets. And this is what MVDR earns: the blue trace, delay in sum, the classic static beamform, and the orange trace, MVDR, same signal, same look direction. But look what MVDR does at minus 40 degrees. This is where the jammer is. It carves out a 40 dB null right on the interferer, which is adaptive and computed at every coherent processing interval, and this is why it matters. And so, the middle panel here, a matched filter output after the static beam. The target's buried, and the jammer swamps it. And now, the same signal after MVDR. And so, as you can see, a clean peak right here at the 30 km mark. And that's exactly what nulling the jammer is worth. And then we have the operator's picture. 2-dimensional Range-Doppler map, after coherent integration. Red squares are CFAR detections landing on the target. But yeah, that's enough plots. So let's actually build this thing. Both models code gen the same way, 1 command each. And so the embedded coder produces Portable C from the block diagram, configured for a reusable functioning packaging, so that each aircraft gets its own autopilot, no shared globals. And the same workflow for the radar. Same reusable function packaging, 1 radar step per site, per instance state, and no shared globals. So yeah, 2 deliverables, Portable C, and this is what flies the aircraft and detects the blips. Each model's generated C then lands in a third-party folder directory on the clearance plugin. The build system detects each one and flips a preprocessor gate that switches the wrappers from stubs to real generated code. The same pattern for both. The autopilot wrapper does 2 things. First, it runs the outer loops, heading to bank, altitude to pitch, and all in C++, because these need wraparound handling and are just simple P controllers. Then it pushes the aircraft state into the model's input struct, calls Autopilot step, and reads the control surface commands back out, which then hands them to the aircraft's dynamics as bank rate, climb rate, and throttle. And the radar wrapper is sort of the same pattern. You feed it a cube of IQ samples, you call the radar step, and you get the detections back. I build that cube on the clearance side, one contribution per aircraft with its range, bearing, and Doppler baked in. Everything after that is just generated code. Okay, so let's get back to the project, which as you can see has been running since the start, before I started explaining the Simulink models. To showcase the Autopilot, I'll command speedbird123 BAW123 right there to turn to heading 100. For the sakes of this video, I'll type it in instead of voice it. The console goes into the simulation controller, which pushes the target heading to the aircraft's behavior object. The wrapper computes the heading error, commands a target bank, feeds flight command into the model, and the aileron comes back out and the aircraft banks. So, as you can see, it settles on the heading, it holds it, and then when it's inside the tolerance that the Autopilot captures, it then stops driving the aircraft entirely. This is so that no numerical noise can excite the loop back into any oscillation, which also causes all sorts of jittery aircraft movements. The same cascade is also on the altitude. The altitude error becomes a target pitch, the pitch error becomes an elevator command, and the elevator becomes a climb rate. And back to the radar side of things. These blips are refreshing twice a second. Each refresh is one full CPI through the Simulink chain, beamform, Range-Doppler CFAR, across every aircraft in the sector. The DSP produces range and Doppler for every detection. My matching layer unaliases range and maps each detection back to its source aircraft. Next up is the jamming. I'll be jamming UAL109. And as you can see, UAL109's own transponder quality return degrades and its data blocks drops the cosine. This is a primary only form of self-jamming. Every other aircraft on the scope is unaffected because the jammer's noise never masks the neighbouring bearing enough to break their CFAR. And that brings it to an end. 2 Simulink Subsystems, both auto-generated to Portable C, both running real-time inside Unreal Engine 5 Defense Simulator that I built. Autopilot flies every aircraft, and the radar signal processor detects every aircraft. The model-based design end-to-end, from analytic derivation through embedded coder to deployment. The repositories are linked below for the Simulink models. However, due to clearance being a work in progress, it will not be linked yet.